All right, so we're moving on. We need to talk about what is the separation of variables, which is going to be the process we use to solve differential equations. So we're going to outline that next. Then we're going to do a couple quick examples, two from the book, and we'll do a couple from the homework section. And then after that, we have one last one of these set up that's kind of physics-based. So we're going to look at separation of variables. Okay. So we got separation of variables, which basically the idea is if you have an expression like this, dy dx equals a function that depends on y times some function that depends on x. So we'll say f of y, g of x. We can shuffle the x dx part from here. We can shuffle that on over. And the function of y, we can divide that back across. And we can get 1 over f of y dy here. And we get that would equal g of x dx over here. And now that both sides, we have only y stuff on this side and only x stuff on that side, we would be able to take the integral of both sides. And this is basically the process of separation of variables. This doesn't solve, like you're not able to use this process to solve every single differential equation, but you can use this to solve quite a few of these. So the first thing we're going to do is we're going to just do a couple examples where we go through and just solve a few of these. So we're going to say, all right, suppose we had y times dy dx minus x equals 0. And suppose from this setup here, we want to find the general solution. The textbook tries to do like 4 examples all at once in this and has like 4 concepts tied together. I think what we'll do is we'll do a couple where we just find the general solution. Then we'll do a couple where we find the general solution with a couple extra bits of information, and then we'll go back and pick up some of the other topics. So we're going to try to solve this by getting the x stuff on one side. So I'm going to move the negative x on over. The dx, I can kind of multiply that across. Or technically, I guess it's not really multiplying, but you can kind of shuffle it on over. And so I have y dy equals x dx. So all my y stuff's here, all my x stuff's on the other side, so I can integrate both sides. So when I take the integral of y, that goes to 1/2 y squared. When I take the integral of x, that goes to 1/2 x squared. And since these are improper integrals, these could differ by a constant, so I need to put a plus c out there. So whenever you do this step here, if you don't have limits on your integrals, which most of the time you don't, after you put the right-hand one down, you put plus a constant after it. So then we say, okay, I need to solve this for y. So I need to multiply everybody here by 2. And this is going to bring up kind of a weird thing that happens in these. So we get y squared equals... Okay, it's x squared. C was just a stand-in for any constant. 2 times c is another constant. So we could say, well, like, okay, 2 times c, let's let that be the constant d. And then, like, if something happens to d, we could let that be the constant e. But what kind of calculus has decided to do is if you have a constant and we do like 2 times the constant and that's still a constant, rather than using just more and more letters, we're able to just call this c again, because this constant is a stand-in here. When it was just c, it's a stand-in for any unknown value. It could be any value. When you have 2 times c, that still could be any value. So instead of keeping track of the 2 times c, we can just write it as c itself. Then to get rid of the square, we take plus minus square root. And we'll have this for our answer. That is our general solution. Now, if they gave me some extra information, I could plug in for y, and we can figure out the constant value, which we'll do that in a little bit. but I want to do a couple of problems where we just find the general solution. So let's look at a couple where we want to find the general solution. We're going to look at problems 15 and 16. So this is 9.115. This will be one of the homework problems. We want to find the general solution. So what they give us is a differential equation. They give us a dy dt. So instead of x's, we have t's. Dy dt minus, hang on, I think I'm working the wrong, I don't think I signed this one. Give me just a second. Let me pull up our classroom thing and just make sure the problem I'm working is the one that I wanted. Let's see here. It was the wrong class. So we're going to do a couple that have us find the general solution. Let me see. The two that we wanted to do, I think I said 15 and 16, but it might have been 17 and 18. These were some that we worked in. It was 16 and 18 are the two I meant to do. So I was off by one. We want to do 16 here and then 18. So problem 16 gives me t cubed y prime plus 4y squared equals 0. Since the y is squared, this is a nonlinear one. They didn't really ask us that, so it kind of doesn't matter. When you have a y prime like this, for the separation of variable stuff, I think it's easier to rewrite this as dy dt. It's easier to keep track of stuff there. This 4y squared, I'm going to scoot that across the equals for a moment, and we'll get that as negative 4y squared. So our expression looks like this for the moment. I need to get my t stuff over on this side and my y stuff back on that side. So the dt is going to come on over here, and t cubed, I'm going to divide the t cubed across. So we get dy by itself equals negative 4y squared over the t cubed. So we divided the t cubed on over, and the dt has slid on over as well. The y squared up top, I need to divide back through by y squared, so I'll end up with 1 over y squared dy equals negative 4 over t cubed dt. So we're at this step. To make these integrals easier to take, we're going to integrate both sides. I'm going to view this, instead of 1 over y squared, that's the same as y to the negative 2, so I'm going to write that one that way. The negative 4 I can push out front of that integral, and this will be integral of t to the negative 3 dt. So we'll go through and we'll integrate both sides at this point. Y to the negative 2, if I add 1 to it, that becomes y to the negative 1. Since there's nothing out here, I need a negative out there, so when I take the derivative and the negative 1 comes down, it hits the other negative that's there, and you're left with positive y to the negative 2. Out here we got the negative 4 out front. The negative 3, I add 1 to it, so that becomes a negative 2. And when negative 2 comes down, I'm going to need a negative 1/2, so when the negative 2 comes down, it cancels with that. And now we put our plus c out there. So let's kind of work on stuff a little bit here. We got negative y to the negative 1 equals negative 4 times negative 1/2 is 2. We could say t to the negative 2 plus c. If I divide everybody by negative 1, this will be, let's just write it all out. This will become positive y to the negative 1 power. This equals negative 2t to the negative 2. And this, we could say if we have plus c and we divide it by negative 1, that's still a constant, so we'll still keep that as just plus c. The last step is I want to get rid of the negative 1 power, so I'm going to raise both sides to the negative first power, and I get y by itself equals 1 over negative 2t to the negative 2 plus c. So we get our expression like that. Okay, so that's problem 16. Let's look through problem 18 and do that one as well. That's another find the general solution. So for that one, problem 18 says we want dy dt equals 8 times square root of y. So I'm going to bring the y back over, divide it back across, so we have 1 over square root of y dy. And the dt I'm going to scoot on over, so we have 8 dt. So we're ready to integrate both sides here. To make this integral easier, I'm going to view this as y to the negative 1/2 power. 1 over square root of y is the same thing as y to the negative 1/2. And over here, we'll just have the integral of 8 dt. When you integrate y to the negative 1/2, that goes to y to the positive 1/2. And when the half comes down, I need a 2 out front to cancel. With this, when you have just 8 by itself and you integrate 8, that goes to 8t. We put a plus constant after it. I want to get y completely by itself, so I'm going to divide everybody in the equation by 2. So I get y to the 1/2 power equals 4t plus c divided by 2. The constant cut in half is still just a constant, so we'll just say that that's still just c. And then to get rid of the 1/2 power, we're going to square both sides. So our general solution to this would be 4t plus c, whole term squared. So that's a bit about going through and using separation of variables to solve a couple of problems. So now that we've done that for a little bit, let's look back at how do we find, let's look back at that example 1 that we did. So I'm going to bring back this first example. I'm going to kind of copy it and bring it on down. So let's say that we have from that first example, we have all this work, we found the general solution, and let's say at this point, now we want to find a particular solution. So we want to say, for this example, we want to go through and we want to, it's called plot a family of solutions. And basically what this means, choose values for C and plot the result. So if we say, let's see, here's our graph. Let's see. Okay. So if C is 0, we get y equals plus or minus the square root of x squared. So that's going to generate kind of a graph that kind of looks like this. We'll have the positive square root of x squared and we'll have the negative square root of x squared. So this is sort of the C equals 0. If C is 1, then we get the square root of x squared plus, let's see here. Let's make this easier to calculate. Let's say C is 4. So if C is 4, we get plus or minus the square root of x squared plus 4. So when x is 0, this is going to generate, this will come down here to 2, and it'll be down here at negative 2, and we'll have our curves. We'll have kind of the plus square root curve up here, and we'll have kind of the minus square root curve down there. So we'll generate those from C equals 4. Next, so we're trying to choose these. So whenever I put 0 in for the x, so if I put 0 in for the x, the equation's easy to calculate. So I'll use 9 next. If I put 9 in for C, when x is 0, I get the square root of 9, which is 3. So that one will come down here to 3, and the c equals 9 case will be like this. And for similar reasons, if we did the c equals -4, that will kind of generate, that'll generate these types. If we do c equals -9, that will generate the ones that come down and touch on the sides at 3. So c equals -9 will be like that. So if you want to plot a family of solutions, basically you choose different c values. A lot of times it's easiest to choose them so that, like, I can tell where like these where these come down and hit the y or the x-axis is why I chose 0, 4, and 9, so that when you put 0 in for x squared, the square root's easy to calculate. Okay, so we said a bit about how to find general solutions. We said if you have a general solution, you can choose different values for c, and you can generate kind of the plot of a family of solutions by choosing some depending on the function, it depends on sort of what spacing of c's you may want to choose. But like if this was didn't have a square root, maybe we would want to do c as 1 and then 2, then 3 instead of 0, 4, and 9. But you can choose c values and generate a plot a family of solutions. If you know what the general equation looks like, then you can get that. So the next example is going to have us go through and say, we want to solve for a general equation, and then we want to go through and figure out what constant c works for that equation. So we have this basically here. We want to solve when is y prime equal to -t times y. So when does y prime equal -t times y? With initial condition, that y of 0 is 3. So when we have this problem here, we're going to use the regular separation of variables. We'll basically use this to find the general solution, which is what we did in the past two examples. That's where you get the y function in terms of c. And then we'll use this statement here, this statement over here. This will let us find the value c. So this will let us find the constant. So let's go through and solve this. Y prime I'm going to write as dy dt. This equals -t times y. So I'm going to move the y across as a 1 over y. I'm going to leave the dy there, and the dt is going to come back across like this, and we'll be able to integrate both sides now. 1 over y integrates back into natural log of absolute value of y. -t will turn into, it'll be t squared. We'll need a 1/2 out front. And the negative's still there, and we'll put the plus c out here. So to get rid of the natural log of y, or to get rid of the natural log part, I'm going to raise both parts to the exponential e. E and natural log will cancel, so I'll have absolute value of y equals e to the -1/2 t squared plus c, where this is all up in the exponent. We're going to do a little bit of algebra now. We can split this up as e to the -1/2 t squared. And when you have a plus there, you can write that as another e to the c. So these are multiplied together now. E to the c is just a constant. So I'm going to replace the symbol e to the c with just c. So we have e to the -1/2 t squared times c, because e to the c is a constant, so we can just replace it with another constant. We'll get absolute value of y equals, I'm going to kind of move the c out front to make this look more like the way we normally write things. Multiplication's commutative, so you can swap the order. Two things are multiplied together. And then when you want to get rid of y, the absolute value on the y, that would create a plus or minus over here. But since the constant could be positive or negative, we're just going to let the constant absorb the plus or minus from the absolute value of y. And we get this right here is our general solution at the moment. So here we have our general solution. And then what we need to do is we need to use that y of 0 is supposed to be 3. So we need to use y of 0 equals 3 to find c. So we're going to put 0 in for t. So if I put 0 in for t here, then the y value should equal 3. Y of 0 equals 3 means when you replace t with 0, the outcome is 3. Well, this now becomes e to the negative 1/2 times 0 squared, which is just e to the 0. E to the 0 is really 1, so this tells me 3 is c. So from here, I can go and say, all right, my actual equation, my particular equation that solves that initial condition is this right here. So I have general solution. General solution gets me down to here. Then I have to use the extra information, and that lets me figure out the particular solution for that problem. We're gonna go and solve one more of these from the homework that deals with finding a particular solution. So let me pull up what the problem is we're going to look at. I believe the one that we want to do is going to be problem 31. So we're going to say, all right, 9-1, number 31. This will be the particular solution problem. This is one of the homework ones. So we get y prime equals x e to the negative y squared. And they tell us the initial condition is y of 0 is supposed to equal -2. So step 1, we're going to get the general solution. I'm going to replace y prime with dy dx. And then I need to start shuffling all the x stuff to one side and everybody without an x to the other. So dx is going to move up here, and the e to the negative y squared is going to come across as 1 over e to the negative y squared times y dy equals x dx. Going to set up to integrate these. If you have e to the negative y, if you have a negative exponent in the denominator, you can move that up to the top, and that would be e to the y squared as a positive exponent. We'd have times y dy equals the integral of x dx. We're going to let u equal y squared, so we're going to have to use u substitution to solve this part. U is y squared, then du would be negative 2y dy. We have y dy here. So I said negative, it should just be 2y dy. So we'll put a 2 there to get a 2y dy. We'll need to put a 1/2 out front to balance. So I will have 1/2 integral of e to the u. 2y dy becomes du, and then that's going to equal the integral of x dx is 1/2 x squared plus c. So I need to actually integrate this side. E to the u is its own antiderivative, so this just becomes e to the u equals 1/2 x squared plus c. I need to replace u with what u is in terms of y, so I get 1/2 e to the y squared equals 1/2 x squared plus c. So now I need to solve for y, and then once we solve for y, we can use this initial condition back up here, and that will that'll let me figure out the particular solution for that general solution. So we're going to multiply everybody by 2. So we get 2 times each of these. So we get e to the y squared equals x squared plus 2 times the constant's just a constant, so I'll write that as c. And apply natural log to both sides because I need to get rid of the e on the right. So I have y squared equals natural log of x squared plus the constant c. To undo the square, I need to take plus minus square root of both sides. And now we're told y of 0 is supposed to be -2. So what I'm going to do is I'm going to substitute 0 in for my x. That's supposed to equal -2. At this point, since it's supposed to equal -2, we can see we're going with the negative value from the plus or minus because -2 can't equal a positive number. So we're getting to see that we're kind of down here to the negative. We get -2 is equal to negative square root of natural log of 0 squared plus c is just c. So now I need to solve this for c. So if I divide both sides by -1, this becomes positive. I can square to cancel the square root. So I get 4 equals natural log of c. Raise both sides to e, and we get e to the 4 is our c. So now that we know the c value, we can go and say y equals, we had to use the negative from the plus or minus. Y equals negative natural log of x squared plus e to the 4th. And that right there should be our particular solution to that problem. Let me check that one against the back of the books. That was, let's see, that was problem 31. I just want to verify that I haven't made a mistake. And let's see. Yeah, and we're good. That's checks out is exactly what they got in the back of the book. So this is one of your homework problems. This is the type where you find a particular solution. So the final thing that we're going to do is we're going to they're going to give us a setup. So I'm going to talk a little bit about the setup here. We basically have a tank. So this is going to be set up for the third example. Then we'll work the third example. So if we have a tank, say like it's a water tank, and this water tank is, let's say it's filled with water up to some height here, and we'll call that height y. Let's say that there's also a hole in the bottom of the bucket, or whatever this tank is. There's a hole there, and so water is leaking out the hole. And if we kind of view the water leaking out the hole, that will kind of form a column of water that's leaking out the bottom of the hole. So there'll be kind of a column of water coming out the bottom of the hole. And with that column of water coming out the bottom of the hole, that's going to kind of drop the water level over here. And so we'll have kind of delta y is the change in the water level at height y. And the change there is going to be based on like how fast and how much water is flowing out the bottom. Will tell us kind of how much drops up here. So what we're going to kind of look at is we'll say if we call A of y the area of the disk here at height y, then the change in volume would be right here would be A of y. So that would be the area of the cross section times delta y, which delta y is the height of the water drop, I guess you could say right there. Suppose that the bottom of the bucket, the hole in the bottom of the bucket, suppose this thing here had area B. And then the column of water, we're going to say as the water falls out, it falls out at a certain velocity. So we'll say it's a velocity that depends on the height of the water in the bucket. So the more water in the bucket, the bigger, more gravity of the water column is pushing down, so the water will come out faster. So we have V of y times delta t. So to represent the V of y, we're going to use It's called Torricelli's law, I guess. And what this says is if you have the velocity of y, that will equal negative square root of 2 times the gravitational constant times the height of your water. So we're going to use that to represent the velocity of the water that's coming out the bottom of the column, which depends on how tall what the water level in the bucket is. So if we do all that, we get down here, we have a change in volume. It'll be the area of the hole in the bucket, and it'll be the height of the water column that's falling out the bottom, which will be the velocity of the water times the change in time of the water. And then what we can do with these two is we can say, well, this and this are going to be the same. This is the volume of water that's lost through the bottom. And so if all the water goes out the hole there, or you get a volume of water going out the hole there, there has to be a similar corresponding volume of water lost up here. So these will be the same. So we can relate A of y delta y equal to B times the velocity of the water times delta t. And we can start working through this. I can divide the delta t across and let the A of y divide back across, and we'll get delta y over delta t is the area of the hole in the bottom times the water velocity divided by the A of y. And if we let the limits on that right there, if we go through and we try to let the delta y over delta t, if we take the limit as delta t goes to 0, then delta y over delta t will become dy over dt. So if the change in time approaches 0, this delta y over delta t will become the, this is like an average rate of change, and this will become an instantaneous rate of change. And we'll get that instantaneous rate of change will be basically solved in terms of this. So we got this equation here from equating the water lost from the bottom, the volume of water out the bottom of the bucket, would you have to equal the volume of the water that drops here. And then we have this Torricelli's law, which is going to tell us some information about how to figure out V of y. So that's some setup in order to do the final problem from the section. So the final example here, they say a cylindrical tank a cylindrical tank of height 4 meter and radius 1 meter is filled with water. Okay. Water drains through a square hole. So water drains through a square hole that is 2 centimeters on a side. So each of the side of the square hole, it's a 2 centimeters by 2 centimeters. We want to determine the water level y of t at t seconds. So determine water level y of t at t seconds. And then what we want to do is say, how long does it take the tank to go from full to empty? So how long does it take the tank to go from full to empty? Okay, so with these types, it's usually a good idea to draw a picture, and on the AP test for types like this, a lot of times they will have a little corresponding picture, but if they don't give you one, it's a good idea to kind of sketch one in. So we got a tank. The tank we know is 4 by radius 1. There's a square hole in the bottom that's 2 centimeters per side. So I need to get, before I really even do anything, this square hole that we have in the bottom here, I need to figure out the length of one of the sides of it, and I need that in terms of meters. Since everything else is in terms of meters, I think the book converts over to centimeters, but I think it's easier to convert this 1 centimeters over to meters. So I'm going to do it that way. So we'll say, all right, we're going from centimeters up to meters. In 1 meter, there's 100 centimeters. Centimeters cancel. So this will be 2 over 100 centimeters, which is 1 over 50 centimeters. So this is going to, sorry, made a mistake. Centimeters canceled, we're left with meters. That's 2 over 100 meters, which is 1 over 50 meters. So this will be 150 per side. So water's going to leave the bottom, and first of all, we want some expression of, like, if you're at a time t, what's your current water level? And then later we want to use that and say how long does it take the tank to completely drain if it started out completely full. Okay, so we're going to basically have to use this equation here, dy dt. So let's pull our 2 equations down that we're going to be using for this. So we got to use this equation, and we got to use that to figure out the velocity. Okay, so let's plug in and figure out everything we know. So we get dy dt. This is going to equal B, which is the area of the hole in the bottom of the bucket. Each of those sides is 1 over 50. So we could say 1 over 50 squared would be the area in the hole of the bottom of the bucket. Let me make that look slightly nicer. So we'd say 1 over 50 squared. That is that substituted in for B. For the velocity of y, this is going to be negative square root of 2 times g, which, since we're in meters and seconds, g is 9.8. And then y is just itself y. What we're trying to do, y is actually, this is going to be the thing ultimately we try to solve for, is so we can figure out y of t, which is the water level at a time t seconds. So that's kind of the variable we're going to eventually figure out. That's all over the area of the tank at height y. Luckily, this tank is a cylinder, so regardless of what height you're at, the cross-sectional area is the same for all of them. It's the same circle. So we're going to use, it's pi r squared. The radius of our tank is 1 meter. So this will be pi times 1 meter squared. So we got the area of the hole in the bottom plugged in, that was here. The velocity we substituted in using this equation here. And the area of the base we did down there. So before I actually use separation of variables, let me algebraically clean this up just a little bit. We want to not round or convert over to decimals till the very end. So we're going to try to keep everything. We're going to try to algebraically clean it up a little bit, but we're still going to have lots of number parts. Let's see here. So this will be 1 squared is 1, 50 squared we're going to leave as 50 squared. So this will, actually, we could do 50 squared. That is 1 over 2,500. We have, that's being multiplied by negative square root of, I'm going to break this square root up as square root of 2 times 9.8, which is 19.6 times the square root of y. And then down in the bottom, we have just a pi. Whenever you all have a fraction in the top, you can push the bottom of the top fraction down below. So what we really kind of have, we could say is square root of 19.6, that's negative, divided by 2,500 pi, and then we have square root of y off here. I'm going to keep this number written in this form. I don't want to take it down to like 3 decimal places. The textbook like immediately rounds this, and their answer has some error built into it because they rounded at this step. If you rounded it at this step and this was like an AP test problem, you would get the answer wrong because you rounded too soon. So we're going to leave our answer just kind of with all the number parts in there like that, and we're going to go through and work on separating the variables. So square root of y I'm going to bring back over here is 1 over square root of y. We'll have the dy. That's going to equal negative square root of 19.6 over 2,500 pi, and then the dt that was here is going to slide across. We'll integrate both sides. To make this integral easier, I want to kind of think about, instead of 1 over square root of y, I want to think about this as y to the negative 1/2 power. So 1 over square root of y is the same thing as y to the negative 1/2 power. If we integrate y to the negative 1/2 power, this becomes y to the positive 1/2. And then there'll be a 2 out front so that whenever the half comes down, it cancels with the 2. On this is all just a number. So if you have the integral of a number dt, you just get the number with a t written after it. And then we put our plus constant. So we're getting close to having a equation. We have a couple of things we need to do. I need to divide by 2 here. So I'll divide by 2, divide out there by 2. I get y to the 1/2 power equals negative square root of 19.6 divided by, let's see here, 2 times 2,500 should be 5,000 with a pi. We have the t. And the constant divided by 2 is another constant, so we'll still write that as c. We'll square both sides to get rid of the square root over here, and I'll get y equals negative square root of 19.6 divided by 5,000 pi times t plus c squared. So we're going to use, they said the tank started from full. Said the tank's filled with water, so it started from full. So what that means is at this point, y of 0 equals 4. So when my time is 0, if I plug 0 in for time here, that will equal 4, because my tank starts from full initially. 0 times whatever this number is, that whole bit is just 0. So I get 4 equals c squared. So we take the square root of 2, or take the square root, so we get 2 equals our constant c. So I'm going to go back and say, all right, my solution is y equals negative square root of 19.6 divided by 5,000 pi times t plus 2 whole bit squared. So I'm basically just using, now that I know c is 2, I'm plugging it back into this equation. And that is our equation that you can input time, and it will tell you the height of the water. So what we found right here is determine the water level at y of t at t seconds. So we have an equation that'll do that. I can input time into my equation, it'll tell me the water level. To finish off, we say, how long does it take the tank to go from full to empty? So what it's asking us is if the tank is empty, then the water level is 0. So it's asking us if we let the water level be 0 in our equation, what time value, what's the t value that correspond to that? So first, to get rid of the square, I take the square root of both sides, so it's gone here, and we get square root of 0, which is still 0. The positive 2 is going to subtract across as a negative 2, so 0 minus 2 is negative 2. So I get negative 2 is negative square root of 19.6 divided by 5,000 pi times t. So now I have the negative 2. I need to get the t by itself, so I need to multiply the 5,000 pi across, and I need to divide the negative square root of 19.6. I need to divide that across. That'll equal t. Negative over negative is positive. And now we'll finally type this into the calculator and see what we end up with for our time. So I get 2 times 5,000 pi divided by square root of 19.6. And that ends up giving me 7096.134 seconds is our time t. The book's answer is a little bit different. The book says it's 7,142 seconds, and they're off a bit because they rounded way back up here. They rounded this number out, or I guess really at this step here, they rounded out what that was and kind of did a decimal approximation of it. And I kept the full bit, so this should do it for this section here. That's the last little bit.